we will consider two symmetry operations. First, a proper rotation, or identity operation, described as C and then a number marked here as n to determine the amount of rotation about an axis. After a proper rotation, excluding a new conformer, the molecule is the same. As an example, we will consider dibromomethane by initially identifying the axis. With a C2 operation, the molecule will be rotated about the axis by 360 degrees divided by 2, so 180 degrees. As a result, the HA is moved to the HB area, whilst the HB is moved to the HA position. What about bromomethane? Here we will consider the axis down the carbon-bromine bond and carry out a C3 operation. The amount of rotation is 360 degrees divided by 3, so 120 degrees. As a result of this operation, HA moves to the HB region, HB moves to the HC region, and HC moves to the HA region. An improper rotation is along a mirror plane. It's a proper rotation followed by a reflection in the mirror plane perpendicular to the proper rotation axis. The consequence of a proper rotation is the same molecule, merely a conformational isomer, but the consequence of an improper rotation is a different molecule. We will examine an S2 process on a generic molecule. S2 is C2 and a reflection. So first, here is the C2 rotation about the carbon-carbon bond axis through 360 degrees divided by 2, so 180 degrees. Now we carry out the reflection about the mirror plane perpendicular to the axis. So what starts out in the HA position with S2 ends at HD. Where we begin with HB, S2 results in position HE, and performing S2 on HC generates HF. What would happen if we performed S6 on the same molecule? So we first carry out a C6 about the same axis, being rotated by 360 degrees divided by 6, so 60 degrees. There is a reflection on the same mirror plane perpendicular to the axis. The consequence of S6 upon HB is that it adopts the HD location. HC is relocated to HE, and HA moves to the HF position.